Welcome people, and welcome back to Kevin Does Physics. So today we've got something a bit different because I'm just going to go through some random physics. Earlier today I did the Unit 2 paper from June 2012. It went reasonably well, but here I've just taken a few of the finer points which didn't go quite so well and made a few slides on these. So yeah, this is useful if you don't really know what to revise. Watch this video and see if you understand what I'm saying. If not, look at some of these topics a bit more in depth. This keyboard. So let's start off with Kirchhoff's laws. This is something that I learned back in like September last year, so I've had plenty of time to forget his laws, and yeah. So the first law is that the sum of the currents entering a junction is equal to the sum of the currents exiting a junction. So let's imagine you have a roundabout and all the roads going into your roundabout are one way. Bit of a messed up roundabout, but it happens. So what you have to think is that all cars coming into this roundabout are going to have to leave this roundabout. There isn't going to be some vortex where these cars massively disappear. They're going to leave somehow. And that is why, as this diagram says, yeah, quite nicely. Kirchhoff then had a second law, one less than Newton. He was a bit of a slacker, but Kirchhoff stated that the sum of the EMF of a cell is equal to the sum of the PD, potential differences, of a closed loop. So let's say here, we take the potential difference of the internal resistance and we take the potential difference of each of the external resistors, and if we sum them together, we get the EMF. Onto something completely different now, which is the de Broglie equation. Literally the final thing in my physics textbook, and it's always an equation that is a bit hidden, because, I mean, lambda, wavelength, that's pretty simple, equals h, Planck's constant. I mean, I know that, but the p on the bottom is what really, in my opinion, stumps, because I don't mentally think of p to be momentum, and that is often why this equation, in the formula book form, you can make it think, what the hell is that? So just a reminder that the de Broglie equation is wavelength equals Planck's constant over the momentum of an electron. Basically, we're saying a faster electron will have a smaller wavelength. This is quite related to the Einstein equation, which we're looking at here, and the work function of materials. The work function of a material is the minimum energy for the photoelectric effect to take place. So basically, any energy below this, no electrons will be emitted. If we have more than this work function, electrons will be emitted, which is what we like. Basically, what we can see is that if you're below the work function, no electrons will be emitted. If you're at the work function, electrons will be emitted, but with zero kinetic energy. If we then apply a greater amount of energy than the work function, electrons will be emitted with greater speed, greater velocity, greater kinetic energy, whatever you want to call it. But it's still important to note that one photon can only cause the displacement of one electron. That doesn't change. And Einstein put this in hf equals the work function plus the kinetic energy. Because hf equals total energy, the work function is the basically energy required to shove that electron moving, and Ke max is the energy left over to make the electron move. And finally, for today's random physics episode, we're looking at the EMF. EMF is the maximum potential difference of a supply, normally associated with chemical power sources, but can equally be used for other power sources with internal resistance. Much like voltage, it could be measured in volts or joules per coulomb. EMF is the energy transferred to a unit charge, whilst potential difference is the work done per unit charge. And EMF can be calculated with the corresponding formulas. So indeed, thank you for watching today's random physics episode. If you liked it, like and subscribe. Bye bye.